This is our second video for Unit 2, and it's on position versus time graphs. What I want you to be able to do at the end is to be able to make a position versus time graph, to be able to figure out the average speed from a position versus time graph, and to describe how an object is moving using position versus time graph. Let's get started. Now, we saw position versus time graphs the other day on our computer lab activity, but you were just kind of thrown into the deep end without really given any type of introduction. So that's the purpose of this video. So the first thing we want to look at is, what exactly is a position versus time graph telling us about? Well, the key is in the name. Position versus time. Remember when we talked about the easiest way to name graphs? We said you can take what's on the y-axis and say it's versus the x-axis. Well, that's what's happening here. On the y-axis, what you have is position. The units for position are usually going to be in something like meters or kilometers. So we want to put those units there. On the x-axis, we're going to have time. And a good units for time is usually going to be seconds. Now let's do an example. Now, what type of data might be on a position versus time graph? Well, you kind of flirted around with this a little bit when you moved our friend Abraham Lincoln back and forth on a number line. So what this is going to show is where is his position on this line at different times. Let's slide him around and see what happens and learn about some of the rules of position versus time graphs. So what would happen if Abraham Lincoln was just standing there? Well, if we look at his position right now, his position is at 0 meters. So where we plot that on here, on the graph, is right here, at 0 meters. If he didn't move, then at time 2 seconds, he'd still be at 0 meters. And at time 4 seconds, he'd still be at 0 meters. And so on, and so on, and so on, if he didn't move. So, what this position versus time graph would look like? It would look like a straight, flat line. Which brings me to our first rule about position versus time graphs. Rule number 1 is that if an object is at rest, the slope of its line on a position versus time graph is going to be 0. What this means is that the line is going to be flat. It's probably worth taking some notes and writing this stuff down. This is probably one of the more difficult concepts, is these motion graphs. Now, another thing we did on the computer lab was to move left versus right. Now, if you look at this number line, right exactly where Abe is standing, that's 0 meters. And if we move him to the right, what's going to happen is that all of these numbers are positive numbers. So for example, if he's starting at 0, and at the time of 1 second, we move him to position of 2 meters, and then by 2 seconds we move him to position 4 meters. By 3 seconds we move him to position 6, then 8, then 10. What we'd have is a line like this. Then Abe would crash into the wall. He'd be standing still, so then we'd move to a flat line. Now if you look at the numbers to the left, all of those numbers are negative numbers. So we could do the same thing and move Abe to the left. 2, 4, 6, 8, and 10. And he'd be moving this way, and then crash into the wall. And what we'd have is a situation like this. So what happened is Abe moved at the same speed, but he moved in different directions. So we had a negative velocity when moving to the left, and a positive velocity when moving to the right. Which brings me to our second rule. On position versus time graph, the sign of the slope, whether it's positive or negative, is going to give us an indication of direction. Now, the easiest way to think about this is to match it up with the computer lab that we did, where left is negative and right is positive. But it could be really anyway. up is positive and down is negative, east is positive and west is negative, south is positive and north is negative, or whatever the rules are that are set. Now I want to try an example where Abe is moving at different speeds. So let's suppose that he's starting at 0, and that each second he moves 1 meter to the right. So at 1 second, he'd be at 1 meter. At 2 seconds, he'd be at 2 meters. At 4 seconds, he'd be at 4 meters. 6 seconds, 6 meters. And so on and so on. And if we drew a line here, we'd see something like this. Now ideally, I'd want to use a 6 and 1 to make this straight, but that would really mess up my iPad and the line would look like crap. So I'm just kind of freehanding it. Now, let's imagine that instead of moving at 1 meter every second, Abe moved at 2 meters every second. So, at the time of 0, he'd be at 0. At the time of 1 second, he'd be at 2 meters, then 4 meters, then 6 meters, then 8 meters, then 10 meters, and he'd crash into the wall and stay the same. So here's what that line would look like. So, what do you notice? This was the one when Abe was moving slow, and this was the one when Abe was moving fast. The fast line is steeper than the slow line. Another way of saying that is that the fast line has a greater slope than the slow line. Which brings us to our third rule. On position versus time graphs, a steeper slope or a larger slope means that the object is moving faster. So those are going to be 3 of the basic rules for our position versus time graphs. We're going to do velocity versus time graphs and acceleration versus time graphs, and they're going to have slightly different rules. But for right now, I want us to focus on position versus time graphs. Let's look at an example of a position versus time graph. So what we looked at before, on the last slide, was where Abe was moving 2 meters every second, or Abe was moving 1 meter every second. Now what you can do with a position versus time graph is to figure out its slope. So if you look at this top line, the fast line, we could pick out this point and this point and say that he had a rise, he moved 8 meters, and the run is 4. So to figure out the slope, you take rise over run. And if you look at this, the rise is 8 meters, and the run is 4 seconds, which is equal to a distance over a time. And if you remember what we've been looking at, distance over time equals speed or velocity. So, rise over run, the slope of a position versus time graph is velocity. And that's how you can figure out the velocity of Abe on either of these lines. Just figure out the slope of that line. What happened here when Abe crashed into the wall? Well then, he didn't move during this section at all. So the rise would be 0 meters, and the run for this whole time would be 5 seconds. And that would equal 0 meters per second. Pretty cool. Now the type of position versus time graphs that you're going to commonly see is something like this, where there's different segments or intervals, and the object is doing different things over time. Let's see what type of data we can get from this position versus time graph using our simple 3 rules. Now just to help us out, I put Abe down here so we can imagine him moving to the left and to the right. So, rule number 1, the slope of 0 means that an object is at rest. So where on here does the line have a slope of 0, or is it flat? Well, that's section B. So that means during section B here, Abe isn't moving at all. Question number 2 says, the positive or negative sign of the slope shows direction. So A has a positive slope, and C has a positive slope. B has a slope of 0, and D has a negative slope. So what does this tell us? Well, that during section A and section C, Abe is moving in the positive direction, or right. And during section D, Abe is moving in the negative direction, or left. And then what it says is that a steeper slope means a faster object. So if you just look at this, what you can see is that section A has the steepest slope. So during interval A, Abe is the fastest. And the one that has the least steep slope is B, and that's when Abe is still. So looking at this, what happened is it took 1 second for Abe to move from 0 to 2 meters right. Then he stood still for the next segment. Then, during the 3rd second, he moved 1 more meter to the right, and then it took him 2 seconds to move back to where he started. Let's do some other calculations with this. So just by looking at this graph, we can figure out a lot of stuff. We can figure out when Abe is moving. Is he moving during section A? Yes. Is he moving during section B? Well, since the slope is 0, since the line is flat, he's not moving. And since there is a slope during section C and D, he's moving for both of those. All right, now we can talk a little bit about the direction. During section A, the slope is positive, so that means he's moving to the right. During section B, he's not moving at all, so there is no direction. During section C, the slope is positive, so he's moving to the right. And during section D, the slope is negative, so he's moving to the left. Now remember, the slope is the velocity, so that's how we figure out the velocity of each section. The rise over the run. And you remember that we can draw a triangle. So in this case, the rise is 2 meters, and the run is 1 second. Rise over run is 2 meters per second. During section B, the velocity is 0 because Abe is at rest. During C, if we draw our triangle, the rise is 1 meter and the run is 1 second, which gives us the velocity of 1 meters per second. Then finally, during section D, the rise is -3 because the slope is negative, and the run is 2 seconds. If we take -3 and divide it by 2, then we have -1.5 meters per second. See how we can do that? You're going to get some practice at this, so don't feel too lost. The last thing that I want you to be able to do right now is to think about the total distance and the total displacement, and then you can figure out what's going on during any section. So if you look at A, the total distance traveled, here Abe has gone from a position of 0 to a position of 2. So that means his distance traveled is 2. Then during section B, he's not moved at all, so he's still at position 2, and his total distance is 2. During section C, he's moved 1 more meter, giving him a total distance of 3. And then, during section D, he's moved 3 more meters from position 3 back to position 0, giving him a total distance of 6. Now the total displacement here, remember, is you're comparing the start, 0, to the finish. So the displacement at the end of time A is 2, because he's 2 meters away from 0. At B, the displacement is 2, because he's still 2 meters away from time 0. At the end of C, he's 3 meters away from time 0. And at the end of section D, he's 0 meters away from time 0. So he starts and finishes at the same spot. Now one thing you're not going to want to forget is to write units. So the units for all of these are meters. One last nifty trick that you can do here is to figure out the total, the average velocity, and the average speed. How you do that? Well, we have the total distance here. And remember, speed is distance over time. So, this whole time is 5 seconds. And to figure out the average speed, you take the total distance, 6 meters, divided by the total time, 5 seconds, and that would give you 1.2 meters per second. Now to figure out the total average velocity, you'd have to take displacement divided by time, and that's going to equal 0 meters per second. All right, hopefully that's helpful. Let's get some practice in, let's take this video quiz, and I think you'll find that this isn't as bad as it seems.